match. It's the match shield they're seniors on teams. Oh, the white one that I sent yesterday. Probably white. What's the vote? The black one, like you can see any of that. It's not well green. Or I think it's like color. I saw last week. It's I make it look like last week. Yours. Which will look like yes. I just wait. It'll stand up because we're already waiting for it. What the stole? Yeah. Let me call it stole. It's sash. There's two different ones. The stole is the one across. That's the shorter one, right? Sash is like the 2024. Yeah, that's great. But everyone's doing white for theirs. Just doing like a basic one. Yeah, we're just signing if we're gonna do the same. Well, it has like the previous years. Are we just gonna get the? We like the way ours looked from last year. I don't know. The black. And rocket like that beside. I mean, as long as in the colors, I think black and white are kind of like the alternative colors. Everything else is kind of like color. It looks. It's this one. Kind of like the space. Well, that's and then this guy. It's either do it just like you guys with a light.
All right, it's 4 o'clock. Let's go and get started. All right, good afternoon, everyone. How's everyone doing today? Good, hanging in there. Almost. Well, you're alive. That's the that's the good part, right? Barely. All right, hanging in there. Almost a spring break. We got one more week after this. Yeah, spring break is a week later. Normally today is the last day, and then we're off on spring break on week 10. But I guess the school thought, one more week. We can do one more week. Yeah. No, I think it's just because the calendar is just all pushed up, and so everything just because of just the way the calendar's been working. So I think leap year. There you go. That's why it's but yeah, so we got one more week after this. So hang in there a bit longer. I'm looking forward to spring break too. Okay, so today another riveting day today. So another we have a little bit of stuff to finish up with 1D equations. I mostly wanted to show you the code today, and so I posted the code for the 1D stuff. So this code is mostly just for you guys to kind of just play with. It's not anything. It's not a required part of the class. If we were to kind of dive in and kind of really look into how this code worked, it would be like another CFD class basically. So it'd be a lot more numerical methods, and I think not. Which is it's fascinating. It's all for those of you who are in CFD. I'm sure it's great stuff, but a little bit too much for this particular class. So I'm just going to show you the code, kind of show you how to modify it, kind of and just kind of talk just a little bit in general how it works. And then we'll wrap things up with the 1D stuff, and then from there we're going to move on to our next topic, which is impedance, which kind of builds off what we've been talking about with the 1D. So it's actually kind of good that we have next week, just so we don't forget all the 1D stuff before we do impedance. But some kind of a lot more kind of the PDEs and things like that. Okay. All right. So some announcements. The only thing that I have you guys working on right now is just your midterm projects, and so I haven't posted any new assignments besides that. So make sure you guys are working on that. If anything, I would at least kind of just try opening up the image data on Computational, make sure that you can read it. I think probably the thing that's going to be the most difficult for people is just kind of figuring out just where to start. So I would definitely at least try to get that started before the spring break, because on spring break I am planning to travel this spring break, so it may not be as responsive over spring break. So I would at least start it just so I can kind of help you look at the image data, just kind of tell you where to start. If you're having trouble with that, then I think it'll be kind of easier to work on it from there. So definitely, highly encourage you guys to at least get started with the midterm project so you can see what that's all about. Okay. All right, so I think that's all my announcements. Are there any questions I can answer before we get started for today? Okay. All right, so last thing that we ended up talking about on Tuesday was we finally finished deriving the 1D equations, right? So it took us like literally an entire lecture and a half to do these things. So probably one of the more lengthy derivations that you've seen in your college career. But we did everything, and so I didn't kind of shortchange you guys on anything here. We did every single step of the derivation, from the Navier-Stokes equations to all the integration and all like the kind of weird math tricks that we had to do along the way, like all those reverse chain rules and things like that. And this is what we ended up with. And so we ended up with this equation here, which you can see is a partial differential equation, two variables, right? So our two variables here are Q and A. And so with two variables, we need two equations to solve them, right? And we have multiple independent variables as well. So we have our solutions are dependent on time t and dependent on the streamwise direction z. Okay, so it's a function of space and time. Okay. But in its current form, we said that there are a lot of difficulties with solving for its solution, right? At the very least, if you can see the terms that I've highlighted in green there, those are our nonlinear terms. So nonlinearity is probably something that's probably been mentioned at least a few times in your previous courses before. But we don't really get into it all too much, especially not at the undergraduate level, just because nonlinear differential equations are extremely difficult to solve. And so we have to kind of do something special with how to solve those, which is where the code's going to come in today. Okay? But before we get to the code, there is kind of one other thing that I wanted to talk about today, which is this term. So in purple there, I've highlighted our pressure terms, which is dP partial P partial Z, right? And so this term has basically just been riding along with us throughout this entire process. This has come straight from Navier-Stokes, and this is our pressure gradient term. Right. So whenever you have an internal flow, like blood flow, right? And when I say internal, that means the fluid is kind of encased on all sides by a solid wall, right? It's the opposite of an external flow, which you would find like over like an airplane wing or something like that, right? Whenever you have an internal flow, almost always your driving force is going to be a pressure or pressure gradient, okay? So this term, even though we've largely ignored it for the majority of our derivation here, is extremely important because this is where our forcing is going to come from. Whenever you have a dynamic system in motion, you need some kind of external force, you need some kind of driving force that's gonna move your object or move your subject forward. And for fluid mechanics, that's a lot of times it's going to be a pressure. Okay. Specifically in cardiovascular flow, this pressure gradient is generated mostly by the heart, right? So when the heart pumps, it creates kind of a spike in pressure, and that spike in pressure drives the blood all throughout the body. Okay. So we need to deal with this because, right now we don't really have an expression for this pressure. But what we do know from all our previous weeks is that this pressure is going to dynamically change, throughout the cardiac cycle as well. Okay. So that's the first thing I want to talk about today, which is the pressure term in the 1D equations. Okay. So let's kind of summarize kind of what I just mentioned. So our 1D equations. Okay. And don't forget, we have two of them. So we have conservation of mass and conservation of momentum. Are primarily solved for two things, right? So we use them to solve for the flow rate in the vessels as well as the cross-sectional area. So normally when you have an extra variable in your equation, usually that variable takes the form of an input. And so that's something that you're going to kind of externally apply, right? The pressure is a little bit different because the pressure actually in fluid mechanics is coupled together with the velocity. Okay? And all that basically means is that, whatever pressure that you compute, even if it's a driving pressure, right? It's still a part of the physics of the situation. So whatever we compute for the velocity, whatever we compute for the flow, it's going to affect the pressure as well, right? And for a deformable wall simulation like we have now, the cross-sectional area is going to affect the pressure as well. So the pressure, whatever we get for the pressure is closely linked with the velocity and I guess the cross-sectional area as well. Okay. And if it's something that's going to dynamically change, if it's something that's coupled together with our other unknowns, that means we have to solve for it, right? It's not something that we can just impose. It's very much a part of the system as all of our other unknowns. Okay. But then this presents a problem, right? And so if we have to solve for it, that basically implies that it's another variable that we have to solve for. It's another unknown. But we're kind of shorthanded here because if we include the pressure, right, that means we'd have to solve for the flow rate, the cross-sectional area, and the pressure. That's three unknowns, right? So in order to solve for the three unknowns, we need another equation in order to do this. All right. So another equation, that they may fill you with a sense of dread because that, maybe that means we have another lecture long derivation that we have to go through, right? Another integrating of Navier-Stokes and more integrals and stuff like that. But thankfully that's not the case, right? So there's another type of equation that we can apply for this called a constitutive relationship or constitutive equation. So a constitutive equation is a lot of different things, and it's one of those things where we're just going to be kind of breezing over it. So we're not going to fully kind of explain it and really appreciate it in detail. But what we're going to be using it for in this case is that it's another algebraic equation that relates pressure to in this case our cross-sectional area. Okay? All right, so this is what we're going to apply here. The fun thing about constitutive equations, or not so fun thing, depends on your on your stance on this, is that there's lots of options available, and so different scientists, different researchers have come up with different constitutive equations that work under different scenarios. And so a constitutive relationship is very much it's very much kind of on the forefront of kind of research and science nowadays. And so people are kind of coming up with their new equations that work under different regimes. And so what you'll see is that a lot of these equations or a lot of these relationships are named after people. So I'm going to give you a couple of the most common ones that are used in cardiovascular, but just know that there's a lot more out there. Okay? So the first one I will show you is by a researcher called Kasab, right? And his constitutive relationship looks like the following. So we have the pressure P minus some reference pressure P naught. This is equal to E, which is the Young's modulus of the vessel wall, times HO. HO here is the wall thickness, divided by RO. RO being the radius of the vessel wall, multiplied by A, divided by AO, minus 1. Okay. So you have a pretty straightforward relationship between, you know, if you look at kind of the two key terms here, everything that doesn't have an O underneath, we have pressure P and cross-sectional area A. Okay, so let me go ahead and label these. And so P is pressure, A, area, cross-sectional area. That's the same area that we're solving for in the 1D equations. Okay. P naught is a reference pressure. RO is the radius of the vessel wall in the reference state. HO here is the wall thickness. And AO, this is the cross-sectional area in the reference state. Okay, so you can see here that, you know, I'm making reference to this so-called reference state one, right? The reference state is nothing more than just, you know, the way a lot of these equations work is that they define kind of changes and pressure change in area from some kind of reference state. So usually the reference state is either, you know, maybe like the average state, so maybe the average pressure in the vessel wall, and everything just kind of deviates around that average, or maybe it's like a zero pressure state. Okay, so usually what happens is that you in your system you measure all of these quantities in one particular state, and then you use this constitutive equation to tell you how it varies from that state. Okay, so that's why you see all these not variables in there. Okay, but end of the day here, you know what you basically see here is it's just a relationship between P and A. Okay, so essentially, you know, we can use this equation as kind of our third equation to solve for together with our 1D equations up here. Okay. All right, any questions on this? E is the Young's modulus. Thank you. All right, so that's one constitutive equation. This is the more simple one, just because it's basically a linear relationship. All right. Number 2, and the one that's actually going to be used in the code, I'm going to show you in a bit, is called the Olofsson model. A funny story. This has absolutely nothing to do with the class, but I you know, when I was first learning this and I was kind of describing these kind of constitutive model, I don't know, because I play a game called League of Legends and there's a character there named Olaf, and so I think of Olofsson. So I thought Olofsson was a guy for the longest time, like for years actually. And then I was talking to like some professor at another university and referred to Olofsson as he, and then he was like, you know, Olofsson's a woman, right? And I'm like, oh shoot, I did not look that up. I just used her model. Okay, so Olofsson's model looks like the following. So it's again a constitutive model, relating pressure to cross-sectional area. Okay, so you have P minus P naught is equal to 4/3 E times H divided by R naught. So you can see it has similar quantities as before, except this right here is 1 minus square root A naught over A. So the relationship between P and A is nonlinear in this case. So the A is in the denominator and there's a square root as well. Okay. but a lot of the parameters have the same kind of meanings as above. So I think historically, I think the Kasab model came first, and then it was used in a lot of non-biological settings. And then Olofsson came along and kind of improved it and found that this relationship is better suited for blood flow. Okay. But it's the same idea for both. Okay. So other constitutive relationships exist, and in fact, there's probably a new one that comes out, every couple years or so. But these ones are pretty respected, pretty well used. Okay. So together, so now that we have the constitutive equations and we put that together with our 1D equations, we finally have the full set of 3 equations that we can use to solve for the unknown flows and areas. Okay. So let's put it all together. So let's look at a code. Okay. So what I provided to you is a set of MATLAB scripts. It's a collection of scripts, and so it's not just one that you can use to solve the 1D equations. Okay? So on Canvas, what you'll find is a zip folder called carotid.zip. And so inside this folder is a bunch of MATLAB scripts that you can use to solve the 1D equations. Okay. So, I provided this to you guys just because, I'm not expecting you guys to be able to implement these solutions because again, that takes a fairly, that's a fairly complex process. You'd have to be taking kind of a course in CFD to really kind of really understand it. And even then, there's still a big challenge, solving a nonlinear PDE. So I'm not giving this to you as something that, you have to really understand everything. But the reason I'm giving this to you is to kind of give you a kind of just something to play with. Right? So just to kind of, you can modify things. And that's what the next homework assignment is going to be about. Where I'm going to give you basically different settings, so different parameter values. I want you to run the code with them, and I want you to comment on the results in terms of why things are changing the way they are. Because when you're learning a new topic like this, right, and this is pretty advanced. We've been doing fairly advanced mathematics, going over very advanced concepts. So when you're learning something like this, it's on the one hand, it's important to really understand the details. I would say kind of get it into the nitty gritty of math, like how the equations come about. But I think kind of equally important to that is kind of, what I call kind of qualitative knowledge of, like, what are you taking away from this class, right? And so if someone is going to ask you, months from now, what did you learn in this class, or give me like a 5-minute thing, right? You're not going to pull out a derivation of the 1D equations and integrate them out your Stokes, right? What you are going to be able to tell them is that, I learned that, if we have a blood vessel and its compliance is this, right? And if we increase the compliance, then it's going to, change the flow waveforms to a certain degree. That's something that you can kind of, that's kind of a little bit easier to digest, easier to kind of, to kind of keep in your brain. And so that's why I'm giving you something like this to kind of play around. Okay. So, it's a lot of code. So I'm going through this just because, I'm kind of bracing you because, we're not going to go through all the code because it's pretty extensive, but, I'll show you where you can kind of change things and kind of how to view the results. Okay. Okay. But before we jump into the code, we have to kind of understand kind of the problem that we are trying to solve. Okay. So we are going to use the 1D code to simulate the flow in this vessel. And the vessel is just something that looks like this. So it's just a straight section of vessel that looks like this. Okay. It's a 1D code, so essentially we're solving for the solution of flow and cross-sectional area in a line. Okay. And pressure. I forgot pressure too. Okay. So it doesn't look like much. It looks literally just like a line. But we're going to be solving for the flow and pressure and area at every point on this line. Okay. So the left-hand side here is the inlet. So that's where flow is going to come in. And then on the right-hand side here, we have the outlet. Okay. All right. So this vessel is going to have a certain length. So we're going to say the vessel has a length L, which you can define in the code. Okay. And it also has a lot of other material properties as well. So we also are going to define the viscosity. That's a kinematic viscosity. The density of the blood, which is rho. We're going to define the reference radius, right? So that's kind of what we needed for the Olofsson model, which is the radius in the reference state. Okay. We also need the Young's modulus, E, of the vessel wall itself. Also needed for the constitutive model, as well as H being the vessel thickness. Okay. All right. And so at the inlet of the model, we're going to have a prescribed inlet flow rate. So this is going to be Qn of T. Right. So conceptually very similar to the lump parameter equations, right? So whenever we had a lump parameter model, we had some kind of inflow condition. This is the same thing here. Okay. And at the outlet, we need some kind of outlet boundary condition. Okay. So I'm gonna do something interesting here. And so for our outlet, I'm actually going to impose a lump parameter outlet boundary condition. Okay. So this is our lump parameter. Lump parameter outlet boundary condition. And in fact, here we have a configuration that's very familiar to us, which is a Windkessel RCR boundary condition. So we're going to find the resistance, the proximal resistance R1, the capacitance C, and the distal resistance R2. Okay. All right. So this is interesting because this is kind of a blending of kind of our last two big units here, where we have, we're solving the 1D equations on one hand, but we're also coupling that together to a lump parameter model. So you have kind of a combination of two different models. Okay. All right. this Q in right here, let me kind of comment on that a little bit as well. Just because you'll see it in the code in a bit. This Q in, is going to be a little bit more sophisticated than our lump parameter one. So from our lump parameter models, usually our Q ins is some kind of sinusoidal function, which could absolutely work in this case. You can definitely do that. But for this particular case, we actually have measurements from a real person of their cardiac output. And so visually it looks something like this. And so it looks like the flow waveforms. And so if you remember, we had that week where we went over arterial biomechanics. We had an image of a flow waveform that looked like this. So on the vertical axis here, we have flow, given in milliliters per second. On the horizontal axis, we have time, which is in seconds. Okay. And that's what our flow rate looks like. So there's a peak, or there's a bump when the heart is contracting. Then there's a little bit of a notch when the aortic valve closes, and there's a little bit of kind of regurgitant flow coming out during diastole. Okay. Okay. All right, so that's our problem set up. Okay. Okay. So a little bit of the theory of kind of, just so you can kind of understand what this code is doing, if you've taken some kind of computational fluid dynamics course or finite element course, this should be very familiar to you. But whenever we're solving a differential equation numerically, what we need to do is we need to break up our domain into different little elements or little nodes. Okay? So this essentially is going to be the mesh of our domain. Okay, so we've basically broken up the domain into all these little dots or nodes. Okay. So this right here is our domain discretization. Okay. And one thing that you'll have control over, whenever you run this code, is the spacing in between each of these nodes, right? So a lot of times, and so let's say in finite elements, we call that the element size. And so you can control how big your elements are. In a traditional finite difference scheme like this, I think they call it the grid size, but it's the same thing. Grid size, element size, same thing, right? And generally speaking, the smaller your element size, the more accurate your simulation is going to be. Okay? And then what's going to happen during the solution process is that we're going to solve for the flow and area and pressure at each one of those nodes. Okay. Okay. All right. So let's enough talking about it. Let's go ahead and jump in. Okay. So let me go ahead and switch over to the screen here. Okay. So let me show you the folder first. And so when you download the folder, it's a zip folder called carotid, because this is a simulation of the carotid artery inside a person's body. Okay? So your carotid artery is the main artery that kind of goes up your neck to your brain. It's very exposed compared to a lot of other kind of arteries there. So it's an important one to know about. Okay? And so inside this folder here, we have quite a few different files here. So you can see here we have files for the RCR boundary condition. We have a file for the inflow boundary condition. Okay. We have a flow that does a Fourier transform of the inlet boundary condition. Okay. So there's a lot of information here for the inlet. Okay. The one file that we're going to be focusing on primarily is the file called carotid. Okay. So let's open up that one first. Okay. So when you open up carotid, this is what you're going to see. Okay? And so the way to kind of interpret this code is that, if you've ever taken a coding class with me before, it's kind of written, it's very much written in my own style, where I have all of the parameters up at the top. And the idea is that, once you kind of define these parameters, then everything else in the code kind of stays the same. So you kind of write the code so that you only have to change just the top part of the code itself. Okay, so let's define kind of the main parameters here. So the first thing we're going to define here is this variable called n per. So n per is the number of heart cycles to simulate. And so by default, it simulates 6 heartbeats. Okay. Next thing we're going to define here is the variable called per t, which is the length of a single heart cycle. So how long it takes for the heart to complete a single contraction. So you need to define those parameters. Next thing we have here is the total time, which is just the product of these two things. So this one you don't have to change. Okay. The last thing that we have here is the time step size, and so this has to do with the accuracy of the simulation. So the time step size, if you've ever done kind of time dependent kind of things like maybe implicit Euler, explicit Euler, Frank-Nicolson, you know that this is kind of a critical variable in that. So this determines accuracy of the time stepping scheme. And generally, the intuition with this is kind of the same as the mesh. And so the smaller your time step size, the more accurate and stable your simulation is going to be, but it also makes it more expensive as well. Okay, so here we have a pretty aggressive time step size. This is 0.1 millisecond. So that's very, very small. All right. And the last thing we have to define here just for the general simulation is the number of cells or number of elements that we want to discretize our domain. And so we're running with 50 elements here, which is a pretty decent for the length of vessel that we have. Okay, next section here, we're going to read the inflow data. And so that's kind of what this part is right here. So there's kind of a lot of functions that are dedicated for that. Okay. So for you guys, what I want you guys to do, in the next homework, once I have it finished, is to, kind of play around with this area. So this is the area where you can kind of play around with the parameters of the vessel itself, right? So you can play around and change the viscosity, you can change the density of the blood, you can change the reference pressure, you can change the size of the vessel. So this is the radius of the carotid artery in centimeters. That's kind of the average radius in the reference state. And you can define the length of the vessel as well. Okay. So what you're going to see here is that as you change these variables here, it's going to change the results. Okay, and it's going to compute some other stuff as well. You can also change the Young's modulus and the thickness as well, but these ones are fairly constant in the cardiovascular system. Okay. Okay. Everything else here you don't need to change because everything else here has to do with the numerical methods or the time step. Okay. Okay, so let's go ahead and run this code, and then we can kind of see what the results look like. It takes a little bit of time just because it's basically solving our partial differential equations. But this is what you're going to see. So you're going to see 2 plots here. And so we have a plot of the flow waveform. So this is Q right here. Okay. So these are Q and we're measuring it at 2 locations. So we're measuring at the inlet and the outlet. Okay. And you can see that there's a difference, right? And so at the inlet, we have a certain amount of flow coming in. That's the blue curve. And then at the outlet, we have a certain amount of flow coming out, which is the red curve. Right? If our vessel had a rigid wall, right, and so our vessel was not able to expand and contract, these 2 curves would be exactly the same because of conservation of mass, whatever comes in has to come out of the vessel, right? But the fact that our vessel here is flexible, the fact that it can kind of temporarily store flow, right? It's almost like kind of like a balloon. You can see here there's a little bit of offset in between these 2. Same thing for the pressure. So we're measuring the pressure at 2 different locations. And so, let me go ahead and draw the vessel here. So we have the vessel here. Okay. So here we have the inlet. And here we have the outlet. Okay. So in the blue, okay, the blue curves here, we're measuring the results here at the inlet. Okay, so those are all the blue curves there. And we're measuring the flow as a function of time. And then in the orangish, reddish, I guess, we're measuring stuff at the outlet, which is this curve right here. Okay. And so we have the same thing for the pressure as well. Let me show you one example of how you can kind of change the code and you can kind of see how these things are going to evolve, right? Let me change the Young's modulus of the vessel walls, actually. Right? And so if our intuition is correct, so if we change the Young's modulus, right? So let's say that we make it more stiff than it is right now. Right? So I'm going to take this, I'm going to multiply it by 10. So I'm going to make the vessel 10 times more stiff than it was before. Then it's going to be a lot more difficult for the vessel to expand and contract. So let's go ahead and run the code. Hopefully it doesn't blow up on me. Good, okay. Okay, so you can see here that once we increase the stiffness, we made the vessel a lot more rigid. So this would be the case where, maybe you have an older person with a calcified blood vessel, their vessels are a lot more stiff, okay? You can see that we have a lot less, overlap between the two vessels here, okay? Or they're overlapped a lot more because whatever comes in has to come out, right? In contrast, if we make this a lot smaller, so we make this, maybe 0.25, make this a quarter of what it used to be. Oops. Shoot. Okay, so we make the Young's modulus, or the stiffness of the vessel, a quarter of what it used to be. We run the code. You can see here that increases the offsets quite a bit because now the vessel can store quite a bit of blood flow, and so you can see that we have quite a bit of difference in between these two curves. Okay. And so you'll see similar differences of when you change the length, when you change the radius, when you change the thickness, right? So each of these are going to have a different impact on the results. And so I want you guys to kind of, download this code, play around with it. I'm going to kind of guide you in the next homework assignment to say, make these changes, see what happens. And you can kind of see what happens from here. Right? All right. Any questions? Yeah.
Is this at like one fixed spot in time?
Yes.
So you're in a fixed space, but you're just passing time at the same point.
Exactly. Yeah. So the blue curve is the blue curve here is at a fixed point right at the inlet of the vessel.
Yeah, that's right.
The other one's at the outlet. Yeah. So good point. So the horizontal axis here is time. So these are at fixed locations, but measured over time.
Wouldn't you expect the pressure to feel like it should show the same profile, but it should be lower at every point for the outlet?
Yeah. No, it's interesting.
But they're like, it's almost exactly the same.
Yeah. Yeah. So there's so if you look at it, you really only have, well, actually, let me change this back to the default. It's a little bit easier to see. Let me go ahead and run it. Yeah, so the question is, shouldn't there be a bigger difference between the pressure waveforms at the inlet and the outlet? Because it's the pressure differences that is driving the flow. So there is a difference here. It's just very small to see. And the thing is with the cardiovascular system, the base or the average pressure is so high that you only kind of need small differences in pressure to kind of drive the flow.
So that tiny difference is all that's needed right there.
Exactly. Yeah. And so if you kind of look at the location, kind of when this difference is kind of maximized, you can see the difference is kind of maximized in this slice right here, which is kind of where this kind of corresponds to this peak right here. Yeah. So it only just needs a tiny bit.
Where the heart beats is when the pressure difference is the greatest.
Exactly. Yeah. Yeah. I had that same question too. It's like, oh, I should be seeing more.
Yeah, I'd expect more area. Like difference between the two of them.
Yeah.
But on the way up.
I had a question about how the constitutive equations kind of solve the pressure gradient. So do they just kind of like take because you mentioned before they had like the reference pressure from like a pressure value at a fixed point, but for the case of the momentum equation, would you use a reference pressure at like a certain z coordinate and then another pressure at like, I don't know, like the outlet maybe?
Yeah.
To solve and then use that pressure difference over like that distance.
So the reference pressure is in this case, what we used here was kind of a steady state case. And so like if there's no flow. And so we basically took the average pressure across the entire vessel and we applied that reference pressure across the entire vessel. But if you want to do it, so there are more sophisticated ways that kind of does different reference pressures for each point, because it's almost never is the blood completely still. But we used the reference pressure with the blood was still. So that's one kind of assumption, one kind of simplification we made. But if you want to do it more accurately, you can do different reference pressures throughout the entire vessel.
So for this one, we did like the inlet pressure and outlet pressure, and then over like the distance between the two.
Pretty much.
Okay,
Yeah.
for sure.
Yeah.
And I also was wondering, can this code plot multiple points like throughout the vessel, like not just inlet and outlet? You could map out like the entire vessel.
Oh yeah.
Pressure and
Yeah. And so if you want to get into it a lot more, there's a lot more you can do with this. And so if you kind of come down to the bottom here, this is kind of the main time stepping loop here. And so the results are actually saved in this in these files right here, right? Q, let's see, Q1 is the inlet, Q2 is the outlet. Where are those saved? So you would have to modify this here. So the results are in these locations here, these variables. And so basically you would output those results from a different location on the vessel wall. And so one right here corresponds to the inlet, N corresponds to the outlet. Ooh, see a little bit of a rookie mistake here to use N here because N is the same as this one, but I made this a long time ago. But basically, you would oh, here it is. Okay, here is the main variable here that has the areas and the flows, and so you would extract that from different locations on the. Yeah. All right. Any other questions on this code here?
Just out of curiosity, but are you using an implicit scheme for the spatial disposition?
It is, yes. And so the scheme we're actually using here is called the generalized alpha method. And so if you want to look at the scheme, there's this other file called normal_solver. So this is kind of where the time stepping scheme is. So generalized alpha is kind of a it's kind of a derivative of Crank-Nicholson actually. So actually if you set certain parameters here, you can get it to be exactly Crank-Nicholson. But we kind of modify it a little bit just because straight up Crank-Nicholson isn't the most optimal for fluid flow. So we kind of modify those coefficients a bit to make it a bit more optimal. Yeah. Okay. All right, so that's the 1D equation. So definitely, definitely check that out. I'll try to have the next homework up for you guys by early next week because I want to include some impedance stuff in there as well. Okay, so let's bring it back here. Okay. So the next section that we're going to start going over, and this will probably take us up to spring break, which is impedance in vascular networks. Okay. So this section right here, impedance to vascular networks, kind of follows, directly after the 1D equations. In fact, we're going to see the 1D equations again very soon, in about 5 minutes. But the idea with impedance is to kind of take the result of the 1D equation and kind of use it to kind of generalize this idea of resistance. Oh, it's catching up. There it is. Okay. So flow resistance, or just kind of this concept of flow resistance, is a very important quantity in just cardiovascular health in general. So not even in engineering. This is something that's talked about by cardiologists a lot, right? And so the idea with flow resistance is, just like the name implies, your cardiovascular system has a set amount of resistance that it has, which is going to resist blood flow. Okay. And that resistance basically refers to how difficult it is for the heart to kind of push blood through your body. So as you can imagine, this is a very important quantity that cardiologists would be interested in, right? Not even just outside of engineering at all. Because the more resistance or the more flow resistance that your body has, the harder your heart has to work, right? And the harder your heart has to work, the more negative health consequences that the patient will generally feel. Okay? So being able to understand and quantify and ultimately hopefully reduce vascular resistance or flow resistance is something of very strong interest. Okay. Of course, the concept of resistance is not new to us, and so we've discussed it a lot in this class in a lot of different contexts. Okay. But we haven't really seen the whole picture. Okay. So far, our concept of resistance or our concept of what provides the most resistance in the body has to do with viscosity. Okay. Okay. So this goes back all the way back from when we did our review of fluid mechanics, right? And so what we said that the resistance in a vessel wall it depends on the radius of the vessel and depends on the viscosity in the vessel, right? Okay. So it depends on viscosity. So the more viscous or more sticky your blood is, the more resistance there's going to be, right? And the radius, right? The smaller your vessel is, the more resistance there's going to be. Okay. All right. And so we first introduced this in our fluids review, but then we talked about it a lot more when we did our lump parameter model, right? And so it's true that it's true that viscosity and radius play a big role in impeding blood flow, but there's other factors that can impede blood flow as well. Okay. Viscosity and radius are kind of easy to talk about because these are what are called steady state effects, right? So if your flow is perfectly steady, right, most of the resistance you're going to see is due to viscous effects. Okay? But when you have pulsatile flow, when you have unsteady flow, when you have flow that kind of changes with time, pressure that changes with time, these unsteady effects can also introduce more resistance to blood flow. And in fact, unsteady effects can give rise to a lot of different phenomena that make it difficult to push blood through. Okay. And so the combination of all these effects, all these unsteady effects, is we kind of lump them all together into a concept called impedance. I always spell this wrong. It's impedance. Or actually, I don't know. I think it might be impedance, but same thing. All right, so have you guys heard of impedance before? You probably heard it before in circuits, right? So it's the same kind of thing, right? And so, I always, for a long time, I didn't understand why, circuits was something that's important to learn as a mechanical engineer. But, the older I get and kind of the more connections that I see with circuits with other stuff, it's important. The thing is, like, circuits kind of gives you a great, I would say, setting to understand how a lot of differential equations perform, even though they don't explicitly talk about differential equations in circuits class. But a lot of those concepts, a lot of those, general behaviors apply to other systems as well. Okay? So we're going to be seeing a lot of that here today, except this is probably going to be at a little bit of a higher level than you've seen before, because we're going to get into wave equations and wave speeds and things like that. Okay. All right. And what's interesting about this is that, we're going to take that kind of that theory of impedance and kind of apply it even more broadly. Okay. And so the theory that we're going to develop in this section here is it's going to give us a platform or give us a way to compute the impedance of an entire vascular tree. Okay. Because the thing with blood vessels, and you've seen this kind of visually in a lot of the images that we've talked about in this class, blood vessels like to branch out a lot. You see, you have a blood vessel coming in, it's going to branch. This one's going to branch like that, right? Okay. Okay. So blood vessels like to split, they like to taper, they like to change size, right? So the blood vessels do a lot of really interesting behavior. Okay? One thing that we're interested in, so let's say that we're standing right here, right? So we're a blood cell, or we're a section of a parcel of blood, right? And we're sitting right at the inlet of this tree, right? We want to know, right? If we're standing here and we're about to enter this tree, how much impedance or how much resistance are we going to experience going through this tree? Okay. So part of that impedance will be due to the size of the vessels and the viscosity, but the fact that our flow is pulsatile, there's going to be pressure wave propagation, there's going to be inertia effects, there's going to be, stored flow effects from the capacitances, right? All of those are going to contribute to resisting the flow from that point. Okay. And we're going to be developing kind of the mathematics that kind of goes along with that. All right, any questions on this so far? Okay, all right. So let's start the mathematics. So we're not going to get through the whole derivation today, but we'll at least kind of start. Okay. So our starting point for understanding impedance is actually our 1D equations, but the 1D equations by themselves are a little bit difficult to use, and so we're going to simplify the 1D equations a little bit. So our first step here is to linearize the 1D equations. Okay. So linearization is a great tool, and if you if you decide to pursue more schooling after this, you get a master's degree, PhD, this is something that you see a lot, right? Because oftentimes, these equations that we have that govern, our physical world, right? Navier-Stokes, the solid mechanics equations, continuum mechanics, things like that. These equations are really complicated. They're really hard to work with. Unless you have like a very complicated computer, right? But if we want to work on with these equations on an analytical scale, to derive new equations, to understand them, they're really hard to work with. So linearization is a technique. If you've never seen it before, this is a technique to take kind of a complicated equation, usually a differential equation, and make it simpler to work with. Okay. We're going to take complicated equations and make them simpler. And the main way that we do this, or the main way that we achieve this, is we take any nonlinear terms, and we turn them linear through some assumptions or through some or certain situations. Okay. So let's look at our 1D equations again. And let's see where we can apply our simplifications. So our 1D equations, so let's start with continuity. So our continuity equation is partial A, partial T, plus partial Q, partial Z. We add those two together, we get 0. Okay. So that equation is actually pretty good. So that we don't have to simplify this anymore. Okay. The momentum equation, on the other hand, is quite a bit more complicated. Okay. So our momentum equation is we have partial Q, partial T, plus partial Z of 4/3 squared over A plus A over rho partial P partial Z is equal to minus 8 pi nu Q over A plus nu partial squared Q partial Z squared. Okay. So these are our 1D equations: conservation of mass, conservation of moment. Out of these equations, if we look at this term right here and this term right here, okay, and technically this term right here too, if you count the constitutive equation, all these terms here are non-linear. Okay. And if you're not sure kind of what makes them non-linear, is that whenever you have the product or the quotient of two variables or two of our unknowns, that constitutes as a non-linear term. So if you look at that first term, the first term is actually very nonlinear. So Q squared over A, right? So Q squared is Q times Q, so that's already nonlinear. then you divide the entire thing by A, which makes it even more nonlinear, okay? Second term, it may not look as straightforward, but we have the product of P, our pressure gradient, and A. If you account for the fact that with our constitutive equations, P is a function of A, then the second term there will be P times A essentially, right? So that's also nonlinear. And then our last term there, we have the quotient or the division of Q divided by A, which also makes it non-linear as well. Okay, so all these terms are non-linear, so they make it very difficult to solve. Okay. So we need to simplify these. So we need to basically provide a way to come up with simpler expressions for the terms that we highlighted. So the way that we're going to do this, it's a very common technique in applied math, is to what's called linearize around a reference state. So we're going to take a page out of our constitutive equations. Okay. And so if you recall from earlier today, a lot of equations are, we like to define something called a reference state. It's kind of like an average state, or kind of like a state where we kind of know everything, right? So it's kind of like an average base state, right? Which is not that uncommon. So a lot of times, when you have a system that's kind of observable, you can measure these quantities in a state where it's known. Okay. And so the main assumption that we're going to make, is that, once we define this reference state, then the changes from this reference state, the changes in flow, the changes in pressure, the changes in area, all of those changes are going to be relatively small. Okay. So when you can assume that the changes or the deviation from the reference state are small, whenever you have nonlinear terms, you're either going to have terms that are going to cancel out because you have the product of two small things, or you can replace one of the unknowns with the reference variable. Okay, which is mostly what we're going to do here. Okay. All right, so if we do that, well, first let's define these. So we have, our three unknowns here are essentially our Q, our flow, our P, our pressure, and A, our area, right? So they are all going to have a reference form, right? We have QO, so QO here is our reference flow rate. You have P, we're going to find P no, which is our reference pressure. And we have area. Which is our reference area. Okay. Okay. So what we're going to do is we're going to replace some of the terms in our equation here by these reference states. Okay. Okay. So let's come back up to this equation here. All right. So first thing, right? So let's look at this first term first. This is probably our craziest equation here, right? So we have the product of Q times Q divided by A. Okay. Waiting for, there it is. Okay. just like magic. Okay. So this is our most nonlinear term here, right? So we have basically kind of a triple nonlinearity. Okay. The other thing I want to kind of highlight here, and maybe I shouldn't have drawn the lines already, is the fact that this term has a z derivative on it. Okay. And so this z derivative, what that's basically saying is that we're taking the derivative of this quantity as we progress from one end of the vessel to the other. Okay. And generally speaking, and we saw this a bit earlier when we ran our code, the quantities don't change all that much in the z direction, right? And so if you recall when we ran our 1D code, okay? And so when you looked at the flow rates, when you looked at the pressures, compared to the inlet and outlet of those vessels, there wasn't really that much of a change, right? And that was a fairly long vessel too. So I think that was like almost like a 13 centimeter vessel long, which is pretty long by blood vessel standards. So what that means is that anytime you see a derivative with respect to z, because quantities don't change all that much in the z direction, this is also going to be pretty small, right? All right, so if you combine that fact, and so you combine the fact that we have a z derivative here, we have a nonlinear term of things that are going to be very small, right? So it's small deviations in flow, small deviations in area from the reference state. Okay, we have a small, this whole thing is going to be small. And so when you have a whole thing that's really small, we can just cancel it out. So that saves us a lot of trouble because that term would be a nightmare to evaluate. Okay. All right. Let's look at the next term here. So the next term, the nonlinearity here is a lot weaker, and so it's not as strong as before. So we essentially have an area multiplied by the pressure gradient, where the pressure gradient also depends on area. Okay. So we're going to perform linearization here. And so since this linearity is pretty small, okay, I'm going to make just one small change here. So for the area here, okay, instead of this being kind of the instantaneous area, which is what A by itself is, I'm going to change this to A naught. Okay. So basically what I changed was that this is now the reference area. Same thing for this first viscous term. So this first viscous term, we have fairly weak nonlinearity. We just have Q over A. But since we're already linearizing around that A naught in the other one, we're going to turn that into the reference area as well, right? So now that A naught is a constant, and we made these terms linear. Okay. So through our linearization process, we've applied we've applied it mainly in two locations. So we made two places where we have the instantaneous area. We're going to change that to the reference area. Okay. Okay. Last thing I'm going to do before we wrap it up for today is we have this last term right here. Okay. So it's a viscous term because it has the viscosity there. And it's the second derivative of the flow rate with respect to z. Okay. We've already said, we've already kind of established that, things don't change that much in the z direction, right? And so when you take two derivatives in the z direction, that's almost like kind of a double whammy of small, right? And so we're going to cross this one out as well. Small since partial z small. Okay. The continuity equation will leave on its own, just that's already linear. All right, and so once we apply those changes here, we end up with a much simplified version of our equations. Okay, so now our 1D equations are, our continuity equation is the same. So you have partial a partial t plus partial q partial z equal to 0. And our momentum equation is partial q partial t plus a naught over rho partial p partial z is equal to minus 8 pi nu q over a naught. So these equations here are much easier to deal with. They're still going to be difficult. There's still partial differential equations with two unknowns and two independent variables, z and t. But now we can actually start to analyze this. So what we'll see on Tuesday is that these equations, we still have a bit to go in the derivation, but these equations are eventually going to simplify to the 1D wave equation. Okay, and so we'll be able to utilize all the good wave equation stuff. All right, any final questions on this before we wrap it up for today? Okay, all right, so that's all we got time for today. So we'll go ahead and wrap it up here. We'll come back on Tuesday and continue on with this. Oh, by the way, so next week I'm planning on getting sick over the weekend, so I'm going to be not here. So I'll be working from all next week. So lectures all next week will be virtual. So you'll probably get an email from me on Monday about how I'm feeling really sick, but just letting you guys, I'm just letting you guys know ahead of time that I'm gonna get sick this weekend. So all right, so thank you guys for coming this week. I hope you guys have a good weekend, and I'll see you guys next week. What's your favorite? Well, you're not even able to like move outside of stuff. One last